Exercise 14.4 is asking you to find the missing reagent you need to create this transformation that they've got here. And if you'll notice, first of all, it's a substitution reaction. Everything stays the same except for this bromine, which is substituted with the fluorine. And so that really means that you need a nucleophile, and that nucleophile is going to be this negatively charged fluorine there. In other words, you need that fluorine to separate from the chlorine so that it could attack this carbon here and kick the bromine off. But look at the reagents they give you. They give you Kf, which is an ionic compound. You have a metal and a nonmetal. A metal and a nonmetal. And so that is an ionic compound, which is really polar. You've got a full separation of charge, plus sign on the potassium, minus sign on the fluorine, so they are really going to want to stick together. And then they give you benzene as the solvent that is dissolved in. We talked about benzene a little bit in exercise 1. It's this 6-membered ring with alternating single and double bonds, or sometimes you'll see it with just a circle inside. And we'll have occasion to talk about that much more later in the course. But the thing to notice about this is that it's really nonpolar. There are no really electronegative elements in this that are creating charges. And so if you sprinkle this ionic compound into this solvent, the potassium and the fluorine are going to want to stick together, because they're opposite charges, and they don't have any other charges in the solvent to stick onto. So we would need, in order to get this fluorine by itself so that it could attack the bromine, we need to coax the potassium away. And you would do that with these things called crown ethers. Now, crown ethers are polyethers, so you've got lots of these oxygens bonded to carbons on both sides of them. And the significant thing about them is that those oxygens are very electronegative, and so they pull electron density to themselves and become slightly, that's what that lowercase Greek letter delta means, slightly negative. And so the cations, with their positive charge, are attracted to the spaces inside of them. They look a little bit like crowns, and you can imagine someone putting this thing on their head. So they're called crown ethers. Oops. So the size of the crown ether, the number of atoms you include in it, allows for different sized cations to fit inside. So potassium is bigger than sodium, sodium bigger than lithium. You could use a bigger crown ether to fit the bigger potassium in it. The way you name these, this first number is the total number of atoms, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Always the word crown. 4 is the number of oxygen, so 1, 2, 3, 4. So total number of atoms, crown, number of oxygens. And what you would need to remember about these is that 12 crown 4 is creates a pocket in the middle of it, the perfect size for lithium. 15 crown 5 creates a pocket in the middle of it, that's the perfect size for sodium. And 18 crown 6 creates a pocket in it, that's the perfect size for potassium. So here, the ion we need to coax away from fluorine is potassium. And the crown ether that could coax it away is 18 crown 6. So we would want to add 18 crown 6. That would steal the potassium. Then you'd have fluorine all by itself. It would be able to attack that carbon. Bromine would leave, and you'd get the substitution reaction. And that's a really significant thing. You would have an ionic salt dissolve in a nonpolar solvent, and you'd have a nucleophile that's really unstable. Fluorine is as small as hydrogen, it's the same size, and you have a lot of negative charge in that tiny space, makes it very unstable. But because you steal the potassium away with such a attractive alternative, 18 crown 6, you can make that fluorine perform the reaction. Okay, here you need to steal, in B, you need to steal away sodium, and the crown ether that's the perfect size to do that is 15 crown 5. So if you add 15 crown 5, it will steal away sodium, and the fluorine will be able to do that same substitution reaction to give you the product. For C, the cation that's stuck to the fluorine, the one we need to peel off, is lithium. And the crown ether that can attract it away is 12 crown 4. Because that's the perfect size for lithium to fit inside of, and so that would steal it away. You'd have the fluorine ion all by itself, and then that could do the substitution reaction. For D, this is not a substitution reaction, but the principle is the same. You still have an ionic compound. Potassium is a metal, right? Manganese is also a metal, but oxygen's not, and in fact this is a polyatomic ion. And so that's an ionic compound that you're trying to get to dissolve in a nonpolar solvent. And normally that would not happen. But here, we could put it into the nonpolar solvent and make it dissolve by giving it some attractive alternative to split it apart. And you might say, well, wait a second, why don't we just use a polar solvent? Well, look at the other molecule we're dealing with. This has no very electronegative elements. Remember, electronegativity increases as you go up and to the right on the periodic table. Nitrogen, oxygen, fluorine, and chlorine are the most electronegative. They pull things to themselves and become slightly negative, and leave whatever they're bonded to as slightly positive. Those charges make things polar. Well, here we don't have any elements like that, so this is nonpolar, and it doesn't have any charges that would let it dissolve in a polar solvent like water. So we can't use a polar solvent for this. Nonetheless, we can use a polar reagent by mixing it in with a crown ether. And the key thing here is to notice here you have potassium, that's the ion, the cation, positively charged ion that you want to steal away, and the perfect crown ether for that is 18 crown 6, because 18 crown 6 creates a pocket inside of it. All the oxygens have that negative charge, and that pocket is the perfect size for a potassium cation, a potassium with a positive charge to fit in. Once that's stolen away, the polyatomic ion here, permanganate, would be able to oxidize or react with this double bond. And so 18 crown 6 is all you would need to write. That would be all you need to make this reaction happen.